Welcome everyone. Good afternoon. Has the summit been encouraging, or have you guys learned a lot from the different sessions you've gone to? Awesome. So my name is Duncan Devore, and I work at Lightbend. A principal systems engineer there, and right now I do a reasonable amount with sales. But before that, I was on the insight team, or the telemetry team, for monitoring, and we were kind of digging into ACA and play and lagom and so forth, and adding points where we could hook in to give some interesting information about how the system's performing. But I'm here to talk to you today about the term microservices, and we're going to talk about it in the context of distributed computing, and most importantly, we'll see by the end of the presentation that what I'm going after is to kind of present to you a view of how identity is derived from behavioral changes which modify state. And in a typical monolithic application, because everything is running in a single, usually on a single machine within some layer, when we think about state, it's a little bit different. It's usually comprised into some type of aggregate, which is going to control an entity. But in a distributed system, that state gets distributed out, especially as your microservices become more granular. And so you have to do aggregations to try to compose state across your different microservices. And that can become challenging. And I think that it's important to understand across a distributed application design where the gotchas are and ways to think about doing that. So that's what my presentation is primarily about. You know us, we invented all play, well, we bought play, but we invented lagom and ACA really is one of our flagship. We contribute to Spark and so forth. And we have some professional or commercial offerings that we have that we call our Reactive platform, or as you see on their production suite. So we used to be called TypeSafe, and now we're Lightbend. Just a little bit about me. I've been programming for close to 30 years now. I started out in COBOL and on a mainframe, and then finally ended up in distributed computing about 8 years ago. We have a book, three of us, called Reactive Application Design, and if you ever decide to write a book, think many, many times before you make that decision. All right, so microservices. What are they? We have heard this term a lot. Probably at this conference, we're starting to hear it more and more. But they do mean different things to different people. So one of the definitions that's common is the idea that you're going to design a chunk of business behavior. You're going to call it a microservice. And the purpose is so you can have multiple teams, right, work independently. They can deploy, they can develop independently, and they can manage their services. I don't know if you saw the Starbucks presentation, but he talked about DevSecOps, where the entire life cycle from the genesis to the death of an application is driven by the team. And that's, I think, a very interesting approach on how to handle things, and I actually see that happening more and more. So the developers are also the deployers, maintainers, the whole 9 yards, and they're responsible for security. Another definition, though, that we can take a look at microservices, we can think about them in the context of this idea of autonomous systems that collaborate with one another. How many people were here for Jonas's keynote? Okay, so some of the stuff I'm going to go over, you will be already familiar with. But I think it's really important when we're building distributed systems to kind of keep these things in mind. So what I'm going to present to you today is microservices more from an architectural design in the notion of distributed computing or distributed systems in general. So this idea of autonomy, right? It's an interesting word. And basically what it's saying is I have a microservice that I'm going to build, and my reality is meaning that I am going to self-govern myself. So what does that mean? Think about, if you think about a group of states that have a loose coupling together and they want to work together, but each individual state has their own laws, their own tax structures and all that, so they can operate independent of one another, or you maybe think of it as like countries, right, in today's world. They do operate independent of one another, but they also operate and interact with one another back and forth. If one of those countries goes down or disappears, right, does that mean the other country disappears? No, it continues to operate. Could there be an effect? Yeah, but it's still operating, right, still working. And that's the way we want to think about microservices and how we design them. So Jonas talked a little bit about this in his presentation as well, but this idea of promise theory, which I think is amazing, just a great application to building these types of systems. So the idea is, in these collaborative systems, you want to think in the terms of promises rather than obligations. And if you step back and you think about this from a human point of view, you realize that this is how life really works, right? Obligations, although we do use them, right? We try to obligate somebody else to do something. If you're a parent, a lot of times you obligate your child to clean their room or something like this. The reality of it is you do not have any control over that person. You can't make them do that, right? So if you tie your behavior to whether or not they are successful in meeting that obligation, you've just really caused a major problem for yourself. If they deliver, everything's great. But if they don't deliver, then your ability to deliver has been impeded significantly, and you could fail at whatever it is you want to do. Conversely, if you say, okay, I realize that this person or this system that I'm dealing with is an independent system, an independent thinking system that lives by its own rules. However, it has published or stated promises that it is willing to, or saying that it will guarantee. So I need to look at those as what they are. What is a promise? Well, I promised you I'm going to do something. Is that a guarantee? Right? No. We'll see. It's not a guarantee. So the health of your relationship with another system ends up being on the number of promises that they satisfied. So one of the things you can do if you're going out, we did this when I was in the energy company. We needed weather data, right? And we kept track of the number of times that we would request weather data from a service. And we were able to come up with a percentage of success. Certain weather providers were not as successful as others. And so therefore, when we began to execute the commands that we needed to pull weather, we ended up going after the providers that were more reliable, right? Essentially, their promise to us was, we will give you weather. A lot of them failed. And that promise may come in the form of, I need weather within 500 milliseconds rather than 2 seconds. And so as we began to work through the process, we began to really understand the differences between a service that we could rely on and we couldn't. And then we had historical weather data that was persisted. So if we couldn't get the weather from any of them, then we could use that data as well. And we could kind of predict what we thought the weather would be. So that service that needed the weather feed never went down for 2 years, even though occasionally we would have problems with accessing our providers. And I think that's a real important aspect, especially when you look at the Reactive Manifesto and we talk about being responsive, right? It's very, very important to be responsive. Even if you can't fully answer the question, you still need to respond back to your customer. So when you begin to think about your microservice that you're in charge of or that you're building, and you begin to think about it in this way, what you end up having is you're gathering your information, you're gathering your critical information, you're gathering your current state information, whether you're using event sourcing or not, you're gathering it locally, right? And by doing so, when you reach out to another service and that promise fails, you will still be able to deliver. It may not be as accurate, it may not be as up to date, but you'll still be able to deliver. And so it provides an a level of certainty and stability for your service that otherwise you would not have. This idea in physics is convergence and divergence. When you obligate somebody, you're diverging. You start at a very well-known point. You're saying, hey, I'm going to obligate you to pick me up at 9 o'clock, right? But as time progresses and things happen, you diverge to an uncertain outcome, right? I may not come at 9 o'clock. And what happens is if that's the only thing that you were relying on because you were obligating me to do it and I fail, now wherever you had to be, you're either going to be late or you're not going to make it there. So the outcome of whether you're able to deliver on whatever behavior you're supposed to, if you've obligated yourself to me, your outcome can be it diverges into uncertainty. Whereas when you look at a promise, you recognize from the beginning that it may not happen. So you're starting at a point of uncertainty, but you construct your microservice such that there are ways that it can get around that. As I gave you an example with the weather, the way that we did weather. So what that ensures me is that while I start in an uncertain location, I am going to converge to a location that is more reliable. And I like what Mary Williams said. She said, promises are not guarantees, guarantees are not possible. And I think because for the last 20 years we've tried to build applications that don't fail through replication and redundancy and load balancing approaches, we kind of get this idea that we can build an application that's going to work, okay? Has anybody in here built an application that has never had a problem? If you have, come see me after the presentation because we want to hire you. But the reality of it is systems are going to crash, even reactive systems. The difference is they have ways to manage it through self-healing or being elastic or something like that. So as I had mentioned, this philosophy or this mentality, a service that's designed like this starts from the premise, and this ripples through the SLA, right? What your agreement is with the business, and what your agreement, and also it can ripple through the way a company thinks about itself in general. So what you're saying is, all right, I'm going to build this system, and it's going to do X, and I'm going to promise to you that the behavior, whatever the behavior is, it's going to be related to X. And that's where I stand. And in order to do that, I may reach out to other services, but I also put in backup or redundancy, self-healing, if those services don't deliver what I ask them to. Because my goal is to keep my service up and running. So one of the things that we run into in this idea that's directly related, now that we have these services that kind of stand on their own, is this idea of state, right? Especially in distributed computing. Right? We'll talk about eventual consistency, but this idea of maintaining state and what do we do about it? In our monolithic applications, it really wasn't a big issue, but in distributed computing, it becomes a problem. And I think the default is, oh, well, we'll just go out and get a clustered NoSQL database, and we'll store all the state in there, and our clustered akka applications will just talk to that, right? And everything will be fine. So just as a side note, we all know what state is, right? You're keeping track of some type of information. You're setting a value that means something. Also, it's interesting with the different ways that you can store data. Hot data, the frequency at which you can get that data is very, very fast, but the volume of data that you can get is much smaller than the inverse with cold data. So I found this slide when I was building this presentation a while back, and I thought it was kind of an interesting slide because we talk about the different types of storage. You know, hot data obviously being in memory, whereas cold is on disk or so forth. So again, when you come to state, you've built a system now, you built your microservice, it's autonomous, you've written the appropriate code to manage self-healing, you've accepted the fact that you know the other services that you're going to talk to, for example, may fail you, and you can't have that bring your service down or make your service not be able to provide the projections it needs for your customers or for your users. Now, the second thing we got to take a look is all right, so the reality of the data that I'm getting from somewhere else, right? What is it really? It's always a view from the past. So when I ask somebody something, okay, some classic examples. It's a terrible story, but a gentleman that I had heard about had decided to take a new job, right? And he received, the notification via email. Yep, your start date will be this. And he started the relocation process. They purchased a new house, and on the way up, going to the new house, he got a call from his boss, or who was supposed to be his boss, and he said, I apologize, but at the last minute, the board denied the request to hire you. So here he is, he quit his job, right? And now he has no job. And when he received that information, as soon as he received it and processed it, it was historical information. And there's a perfect example. So he said he looked at that information, as probably most of us would in that scenario, but he looked at that information as like a global state of now, right? He got this email. When we're building systems, however, we need to realize that. We need to realize the data that we got from the whatever external service it is definitely a view of the past. For us, when we did it in the energy industry, it was blatantly apparent. We had to do predictive analysis, and we had a 2-week sliding window, and we were using time series data. And we were doing real-time graphing of energy consumption for a campus and where they need to keep their energy usage or what have you between a particular upper and lower bound so that they could either save money or make money, right? And oftentimes the building automation system was unreachable. Meters on something were unreachable. We're processing tons of data, but did we say, okay, if I can't reach picometer 227, I can't draw my graph? No, not at all. We had algorithms for smoothing that data. If I get 4 readings from that meter saying it's 65 degrees, and then I get a reading that says it's 180 degrees, right, and we get readings every 1 minute, am I going to draw that on my graph? No, that's a little weird. There's no way the temperature jumped that much. And then the next reading is like 5 degrees, so something's wrong, right? So we had an algorithm that walked across a 5 or 10 minute span that would smooth the data for the meter, and we basically wrote our own anomaly detection. And then after we had a certain number of those, we would make a decision to say, hey, this meter doesn't work anymore. And so we have to alert somebody. So we were able to avoid alert fatigue, because imagine if every time we read that spike, we sent out an alert. It's like a car alarm. Eventually you stop, you just ignore it. How many people pay attention to car alarms? I mean, I'm in New York City. I hear them go off all the time. So this is a very important concept to understand. Also, with Amdahl's law and Gunther's law, the whole idea of trying to maintain a global state of now, it just really is impossible in a distributed environment. You have latency, and it doesn't matter how much you go out and parallelize things to expedite that. There is a curve where you end up just degrading, and your view of this global state of now just starts to crumble. And I love this slide. As the latency gets higher, the illusion cracks even more. So, how many people have heard of Pat Hellen? Good. So you guys know who he is. He's awesome. I hope to meet him someday. But he's a really awesome distributed engineer. And he says this. He says, where the work is done, you can know where it's done or you can know when it's done, but you can't know both in a distributed environment. When you step back and think about that for a second, it's like, wow, okay. How do I deal with that in life? We kind of do it to to use Scala terms, implicitly with human relationships, right? We kind of accept that unless we have mental problems or we're codependent or something like that, right? I mean, sure you've read about that stuff, and that's where that kind of breaks down. We don't accept this type of reality. But normally, when we're healthy, we accept the fact that we know where someone may have done something or when they may have done it, and then eventually we can reconcile the two, but we don't generally know it all at the same time. So because of those things, and because of the way we're dealing with building out distributed systems, we have this perfect storm that occurs that once you cross over that boundary of your microservice into no man's land called the internet, who knows what could happen. I've seen DNS problems where the same code set that is running on one data center, not too far from another data center, maybe 25 miles at max, right? So customers would be routed into the closer data center. They can't get to the database because there was a DNS problem. Had nothing to do with the code. Trying to find that problem was a nightmare, right? And back then we didn't think about rerouting traffic over to the other data center. You know, this was like 10 years ago. But that's the kind of stuff that can happen, and it can take day. I think it took a day to fix that problem because we had to go through 3 or 4 different vendors to find out whose router it was, right? Because back then there was a million ISPs. And we finally found it through doing a whole bunch of packet sniffing and trace routing and stuff. But all kinds of crazy things can happen. And that's why the notion of the way we build reactive systems with elasticity and resilience becomes really, really important. It becomes crucial. Our island, however, is a microservice. So let's start out just looking at it from a local perspective. The reason it's really powerful is one of the things that you want to do is ensure that your application works. And how do we do that? What is the way that we ensure our application works? What's the number one way? It starts with a T and ends with a T. And there's an E and an S between the T's. Right? And it's prefixed with either unit or integration. I had the pleasure, does anybody in here know Mike Pilquist? Mike Pilquist is a fellow at Comcast, and he's one of the best engineers I've ever met in my life. And I worked at him with Comcast for about 2 years. And in working with him, I learned quite a bit of different things, but one of the things that I learned was essentially the pre-reactive belief, right? So we were building OSGI systems, and I forget what I was doing, and he looked at a piece of my code, and he said, Duncan, you can't do that. And I said, well, why not? I mean, it makes perfect sense. He says, because if that system doesn't go down, then you don't work. And I was thinking about it, I'm like, wow, okay. So what do you want me to do? I mean, where else am I going to get the data? He's like, you're going to have to cache some of it historically. So what we'll do is you'll do pools, we'll set it up locally, and we'll cache that, and that'll get done every 10 minutes. And so you will at most be 10 minutes behind if your call fails. It was brilliant, right? That service never went down. So how do you do that? I get asked this question all the time. I want data locality, right? I want whatever mechanism I'm using for my data to be stored on the same node as the actor that's accessing it. Well, that's really hard to do unless you store it in the actor, right? But what we will say is the diagram on the right, and forget that little data pump box, but the diagram on the right is a microservice for whatever it's going to project should own its data exclusively. And this idea or this design pattern, it can be a little bit difficult to embrace, right, if you think about it. I talked to a customer 2 months ago, and they had a really nice reactive architecture set up, and everything went through multiple stages, through play, and did some ACA streaming and everything. And I think that whole request going in up to point X took like 100 milliseconds. When it hit X, it made a call to the mainframe. It took 7 seconds to come back, right? And so I'm talking to them, and they're like, what are we going to do? And I'm like, well, you have a problem, obviously. One solution, is there any way to go to your mainframe provider and do whatever you got to do to fix that 7-second delay? And they're like, no, not really. And I said, okay, what have you done to try to get around it? And they're like, we've done caching. It used to be worse. It used to be like 14 seconds. And I said, okay, well, there is a way you can get around this. You can basically replicate the data in small time chunks, right, in something like Cassandra. And then they'll make the call and they'll hit Cassandra, and they won't hit the mainframe. The only reason they'll hit the mainframe is as if for some reason the Cassandra payload is exhausted or is past the time boundary that they're asking for the data in. So that will drastically reduce that latency. The whole transaction will be under 1 second. And they looked at me like I had 5 heads, I kid you not. They're like, are you proposing that we have duplicate data? And I'm like, yeah, that's exactly what I'm saying. How else are you going to solve the problem? If you know another way, tell me. Right? And if you think about it in real life, we do things like that all the time, right? If I'm going to put mulch down in my yard, do I go to the store and buy 1 bag at a time, come back, dump it, spread it, then drive back to the store and buy another bag? No. I either go to the store and buy 30 bags of mulch, or I call up a landscaper and say, hey, bring me a ton of mulch and dump it in my driveway, right? I bring that data, the mulch, closer to me. So then, and it's the same thing in these types of scenarios as well. It's thinking this way, I think, is hard. Another good thing, just for structure purposes, that Pat said was our current present, what we have inside our microservice, that's what he calls inside data. That inside data is our view of now. That is our reality. Outside data is from any other place, is historical, a blast from the past. And I like what he said about between, when you ask the question, it's a hope for the future. That's the reality of it. And in our architecture design, if we don't realize that when we ask that question, that we're hoping to get an answer back, as opposed to, oh, we will get an answer back. Like whenever I have to have guaranteed message delivery, right? Really? Are you sure about that? Let's talk about that. What are some other ways that you could approach that so you don't put that what's the word I'm looking for? So you don't bog down your system by having to persist every time you send a message. So these concepts, I think, are really important. Now, another way to say this is, or another way to do this that I often hear is, well, no problem, we're going to create stateless microservices. And then we're going to dump all the data into our go-between, our queue, right? And yeah, that is one way to do it. But I argue that your applications aren't stateless. You're just pushing it onto somebody else and making them responsible. Furthermore, I think when you design a system, the system has to be knowledgeable of whether or not something occurred. So if I'm going to publish an event to a queue, I want to know I did that. I don't want the queue to manage that for me. Maybe you'll have the queue manage it for me and I'll know that. That's fine. But I'm going to know it. And if I don't get the response that I expect within the time, I'm going to publish that message again. And on the other side, the recipient is going to be idempotent. So if they already received that message, they're going to ignore it. They're going to drop it on the floor. And so thinking this way is how you start to build these high-performance systems. It's exactly how we work as human beings, right? We're the most advanced computers in the world. And this is how we work with each other. So why do we try to build systems that expect or obligate each other? And it's really a fascinating thing to step back and think about it. So obviously, the way that we get around this stuff is through eventual consistency. How many people in here have written a distributed system using event sourcing? Like in anger, right? You went through all the stuff and you learned, right? Okay. So I've done a lot of it for years, and it's a very interesting concept, and I'll show you an example here, I think, which will kind of explain it. But one of the realities is that the data between points ends up being eventually consistent. And obviously the definition is if nothing changes on node A and nothing changes on node B, then eventually the projection on those nodes are going to be consistent. They're going to be one and the same. So the first thing we think about, wow, that's not good. So two things. First of all, people will say, well, what is the time to be eventually consistent? And my response is, I don't know, you tell me. What's the SLA say? Well, the SLA says 500 milliseconds. Okay, then it'll be 500 milliseconds. If they say it's 2 minutes, and then I'm like, okay, it'll be 2 minutes, right? And then you strive to write your code so that happens. The other thing is our lives are eventually consistent. Anybody in here ever have an overdraft? Right? Why? Because your bank reconciliation was eventually consistent. So you drew money out of the ATM, your account went to 20 bucks, and then somebody wrote a check for 50, and all of a sudden, your bank is minus 30 plus a $15 overdraft fee. That's how it works. You ever order something and it's back ordered? Right? Well, back ordered? How could it be back? How could it be, back ordered? What is, we're in the 21st century or whatever. So, with many of our critical systems are eventually consistent. So no one wants it. It's evil, but it's a necessary evil. So one of the things, as we saw on that other side, is, all right, so now that we got all these concepts, we know about obligations and promises and autonomous behavior of a microservice. We talk about storage. We say polyglot persistence. Use whatever storage mechanism makes sense for your microservice. Sometimes that's Cassandra cluster. Sometimes that's Redis. Sometimes it's in-memory some sort of in-memory database. One of our other coworkers, Doug McPherson, gave a presentation yesterday, and he's been in the cellular industry for a long time, and he rolled out an Akka cluster in the largest cellular environment in the world in India. And they have like 9 data centers, and all this stuff's clustered across the data centers independently and becomes eventually consistent and everything. And one of the things that he used was Akka distributed data. So, I mean, there's a lot of different ways that you can store your data, but what I would argue is, don't just default to one because that's what you're used to. Now, I understand that sometimes in your company you may be restricted and you have to use Oracle or you have to use, Mongo or whatever, but if you can, don't you restrict yourself to that. And so Jonas said this yesterday, is the other thing too is we look at a lot of times the database is the source of truth. But in reality, if you're doing auditing, even if you're in a CRUD model and you're doing auditing, the aggregate view of all the logs across your application is the real source of truth. The database, if you're doing CRUD, is only the current state at that moment in time. And so he's saying, why do we look at the database in that scenario? Why don't we just use the logs? And he's talking conceptually here, right, in theory. So what he's talking about is event sourcing. And I love this canonical model here of event sourcing, as Greg Young says it. And he made a really interesting statement. He said, more mature business models use this type of structure for storing data. And so obviously accounting is a pretty mature business model. It's been around for a long time. And I mean, you can see debits and credits. You can at any point go back and you can say, what was my balance on the January 4th, 2012? What was it on January 3rd, 2012? You can do that because you have all the data that you need. If this was just a current state model, then you could never do that, right? Because All you would do is update the current balance. And that's my example. As you can imagine, if you're reconciling your checkbook, you say you have $10,000, your bank says you have $3, that would be a problem. You call them up and they say, oh, I'm sorry, when we developed our system, we use a CRUD, it's current state model. We don't keep track of debits and credits. Now, I mean, obviously that's ridiculous, but it kind of brings the point home of what I'm trying to say. And so this is, again, one of the things that Pat argues for. So an example that we use in regards to this, and this all becomes very important when we get to the end of the presentation about identity composition. We have a CRUD shopping cart, and in that shopping cart, customers order, they add a bunch of stuff. They get their shipping information, a total is generated, and the order is inserted. And then at some point, before the order is shipped, the customer logs back in and deletes one of the items, right? So you do a deletion from the order line table, the item's gone. So this is what, after the deletion occurs, this is what it looks like. We have an orders table, and we have a total stored in there, and then we have the order line table, and then maybe another table for shipping. And that's kind of our structure. When the customer first did it, there were 4 items in the order line table, but now there's only 3. Related, the related key back to the order itself. Now the manager comes in and he says, we have a particular product that we believe is being removed when customers go to purchase it, or we're not sure, but I want you to keep track of any products that are removed from, I want you to give me a report on products that have been removed from the shopping cart. And your answer is, we can't do that. We don't have that data. What we can do is we'll implement hibernate and vars, right? And we'll implement auditing, and we'll capture that all in an audit table. Great, it'll take us one sprint. We have fantastic Java developers, and they're really good at this. And it will work. We'll write all kinds of tests. And so you do that, and you deploy it, and it works. But you have another problem, that there's no way you can get around it, right? You can only use that new data that you're capturing from the point that you deployed it on. So there's a lot of historical value to customer behavior that has been lost, and there's really, really no way to get it back. So the reactive shopping cart looks like this. It's a little bit more robust. And are you guys familiar with events and commands and the way that they're structured? Let me ask this, is there anybody that isn't? Okay, so I won't go through all the details, but you basically have commands that come in. Those commands get processed by a command processor and turned into events. And the one command can get turned into multiple events. It's up to you. Now, the usability of your system depends on the granularity of your events. So if you have one event, stuff happened, it's not going to be very useful, right? But if you have product added with the product number, product removed with the product number as an event, then you're going to be able to derive a lot of information from your data that you otherwise would have not. So we go through the same example. Stuff is added to the cart. We have an event stream now that is inserted. Everything is an event added to some database. We have the same scenario. A customer comes back in and deletes an item. And that delete is entered as another event, right? The nice thing about this is that this structure allows you, well, real quickly here, the way that you derive current state is you replay all those events, and for optimization purposes, you implement snapshots, right? Because if you have 100 million events and that actor crashes or that object crashes and then you spin it back up, you don't want to have to replay all those events again. So you'll snapshot its current state, and that will be stored in some table, and then when the replay occurs, it'll go get the last known good snapshot and then play all the events from that point forward. The technology implications of this structure are really cool because it's additive only. The key is basically a hash And so as long as your hash is written correctly, then sharding is really, really easy. And you can have your database clustered and so forth. So that makes this model really powerful for distributed computing. You have almost no locks or a lot fewer locks because you're just doing inserts. And so from that perspective, it's great. But even more importantly, right, from a business side, you are tracking all these events as from inception, and you can answer questions from the origin, assuming that your event model is granular enough, from the origin that you first rolled the system out. And what's even more fascinating is you've put yourself in a position where you could potentially answer questions that have not been asked yet. So if the original team that wrote the CRUD shopping cart had used a reactive shopping cart with event sourcing, when their manager came in and asked them to do that, they would have been able to write some quick code to generate a report or something or a projection, and they would be able to do that. So before I go into the end of my presentation, the other thing that I wanted to say, who's here familiar with CQRS? Good, a lot of people. I built these systems about 7 years ago, and back then nobody ever heard of it. And it took me 6 months to convince my company to let me do this, right? And now it's becoming much, much more popular. And I love CQRS because I can basically create projections, aggregate views across all my sources of truth, my write sides, and I can optimize them. And at the energy company, it didn't matter how nasty the query was. We had optimizations that were running all the time in the background. But because we would capture the results and then store them in a projection-friendly view, when a customer went to a particular place in our application, those graphs would just stream real time. Right? We didn't have to execute the query because the query was already executed in real time. It was always being executed in real time in the background, and that everything just flew perfect. It was amazing. So this brings me to this whole idea of composable identity. One of the first things that you need to think about are transactions, right? In a distributed systems, transactions become a real big problem. So my goal when I built this back then was I want 0 transactions. We had tons of transactions. And they're like, it's impossible. And I'm like, it may be, but I'm going to try to find out a way to do it. And what we ended up doing is as we split out our microservices, you know how in Spring or with JDBC, or not JDBC, but I can't think of the name of it now. What's the Java interface for databases? Not JDBC, but what is it? JPA. Yeah, that's what I was thinking. In JPA, you end up having these bidirectional relationships and lazy loading a lot of times. And you have to add on your, when you pull it from your domain object, you have to add, ignore lazy loading because you get into this infinite loop. It's just nuts. And so what we did is we pulled everything apart. We had unidirectional relationships where the child would have the parent's ID, but the parent knew nothing about the child. This is the exact same problem in open tracing and how we solve it. Because time, clock or taking a timestamp is not good enough because they could be out of sync. So you have to have an ID in there too so you can recreate what's going on. And so, as a result, we got rid of almost every single transaction that we had. But if you haven't read this paper, you should. It's a really good one, Life Beyond Distributed Transactions. So it brings me to this final slide here. And in this final slide, you can take a look at this one of two ways. You can say that's a single microservice, and those boxes that say state in them are entities or aggregates, aggregate and entities, one and the same. Or you could say they're separate microservices, and that the big box on the right or on the left there is a projection of the entire application, right? So if it's human resources, there could be a lot of different microservices that support human resources. Either way, you're having this idea of composable identity now because you split out across. The thing that you have to remember is that identity is relative, right? It's temporal, is what I should say. And I'll give you the example, I think, that makes it real easy. Let's say you're a rugby player. Anybody in here play rugby? Awesome. I've never played it, but I used to play football. But you're a rugby player, and you're good. And so you're out there, and what is your current identity? Your current identity is, I am a rugby player. And that's what, right? Why am I a rugby player? Because the state of my body is healthy, and my behavior is that of playing rugby. Now, while you're playing rugby, you have an unfortunate accident, and you break your ankle. Okay? So, what happened? Well, your behavior while playing rugby ended up doing something that caused you to break your ankle. So the state of your body changed from healthy to unhealthy. As a result, your identity changed. You are no longer a rugby player. You are now a patient. Okay? And that connection between those three things, behavior, state, and identity, are very, very important. They also get aggregated as a team. If enough rugby players break their ankles or are taken out, they're no longer able to play the game, and those groups of individuals are no longer a team. I don't know what they are. They're half patients and half guys that wish the other ones hadn't hurt themselves. But do you see what I'm saying about that aggregate identity? And understanding that and thinking about that across how your application works is, I think, one of the most fundamental things that you can do. And you got to think about how that works with your customer and their behavior. So that's it. Those are some of the lessons that I learned over the years, and I hope that is helpful to you. And we have a couple minutes if you have any questions. Feel free to ask. I think there's a mic here somewhere.
Hello?
There you
Oh,
go.
much better. Okay. So you mentioned about projections, right, in the context of CQRS, right, command query responsibility segregation.
Yep.
So as I understand it, projections are really good for when you want to run ad hoc queries against projections from multiple streams.
Yep.
Are there other use cases that you found as well for projections, or is that pretty much?
Well, what I realized was as I built out several different systems, some for our clients, and then obviously for what I did at the energy company, when I went through all the questions that we were going to ask, we ended up knowing something like 98% of them, even when we were doing statistical regression and we were training, right? So we knew what the query was going to be. The statistical regression or the optimization ones were a little bit more dynamic, but they were static. This is crazy. They were statically dynamic. In other words, they would be whatever the data scientists wanted at that moment in time. Then they could go in and they could change the equation a little bit and then redeploy it. But at the end of the day, whatever that equation was, that's what it was, and it ran that way. Probably only 2% or 1% of our equations were truly dynamic, where not just the variables that are coming in, but the question itself is changing. But what I realized is that type of questioning was usually on the other side of the fence, had nothing to do with their application. It's when the data scientists were training the application. So as a result, I could run these queries in the background all the time, and slowly when I say run queries, is an event occurs, I throw it over the fence to anybody that wants it, they pick it up, and they know how they want to aggregate that data and store it in a table. And that's what I mean by that.
No, it makes a lot of sense. Thanks. And just a quick follow-up question. So I think what you're describing lends itself really well to some sort of an iterative process, right? Where you don't have a lot of dynamicism going on, but you want to kind of tweak the same kind of model over and over, like Spark does and stuff. So.
Right.
Okay.
Yeah, absolutely.
So I asked this question a little differently on the keynote speech. Is it a good idea for the right side of your CQRS equation to actually be just stored on the stream itself, the streaming backbone? Like all your events on the stream, left on the stream, and obviously your read side is you stream it off into some other structure that makes more sense for whatever your application is. But can you foresee a major issue with that, or is it just a bad idea to begin with?
So I want to make sure I understand your question. Can you say it again? Is it all right for the right side too?
Is it okay if on the right side of the CQRS equation, and assuming like an infinite stream depth or infinite stream retention period, is it a good idea to use the actual backing stream being Kafka, or as we've heard, Pravega, or something similar?
Yeah, I mean, yeah, there's nothing wrong with that at all. Okay. Not at all. And I will suggest to you there's also a hybrid view of CQRS. On the right side, you generally store inside the actor the current state of that entity in memory. So if I have an employee, I'll store inside the right side's actor, the weight, height, eye color, salary, whatever you store in regards to an employee. So one of the decisions that we made was, initially we started throwing that same data over the fence and storing it on the read side. I'm like, wait a second, we already have it here. Not only do we have it here, it's in memory. So let's kind of be rogues, and if you have a question about a particular employee, we would go to the right side. And I know it's blasphemy, but that's what we did, and it worked beautifully. A purist would say, that's horrible, you should construct that over on the read side. But any kind of aggregate view of anything was always on the read side.
So a follow-up question there. If you're, for example, you are replying in a, God forbid, blocking manner to some request coming in over an HTTP or some sort of channel, I have to respond within a certain time frame. So I make an event which changes some value of my state. I emit an event for that. Then, I mean, in a purist sense, I'm going to wait for that to go around the houses and back into my read side so I can respond with the change to my customer or client. Is there a nice way to kind of short-circuit that for this kind of scenario? Or is it a good idea to actually just wait and follow the pattern?
Yeah, so if I understand your question correctly, to get around that, what we did is you would update something, right? Like, I don't know, maybe you change somebody's address. That would go through the right side. But the result of that would take you back to an aggregate view, and that address had to be replicated in that table. But that aggregate view was in another location. So the right side would send back a token that on the front side, we use Node.js, it would then execute that, which would automatically take it to the right read side. And so there was this little bit of latency, right? Because if the read side had not digested the data yet, then the screen would be incorrect. So we had a kind of like a monitor, not a monitor of messages for ACA, but a monitor to determine whether that read side had been finished. And if it hadn't, then you get your little spinner. So that was probably, I didn't even think about that when we built the system, and my front end guy comes back, he says, look, dude, look, boss, this isn't going to work because that other data is stored over there. How are we going to get around this? And so that's how we ended up doing it. That worked pretty well. Yep.
Hi. So with CQRS and event sourcing, isn't there like always a small window of time where you might miss writing the events to the fact that we send the data to the CQRS, and would it be possible then to send multiple updates to the same update in case of a crash or loss essentially of the log? So a system as simple as sending increments of +1 would have an actor. It says, I got that message, you write it down to disk, it persisted somehow, then you send the +1 to your CQRS, and then just after you've done that, your system crashes and doesn't have time to record the event, or vice versa, you record the event first, and you're missing the fact that you sent a bit of information. So how do you deal with such scenarios? Do you just accept them, and how do you deal with such types of
right,
scenarios?
the eventually consistent read with the write that just occurred?
Yeah.
essentially. Yeah, well, I was just describing with him, we used a token, and then the front end was smart enough to ask, and if it didn't get the expected update, if the token hadn't reconciled on the read side, then it knew basically to put a spinner up. And it usually reconciled within 30 or 40 milliseconds. And so that spinner almost never occurred. In fact, to learn is it works so well that when the spinner did occur, there might be some other nefarious problem going on. But that brings another issue is on the right side, how do you resolve conflicts, right? And so my recommendation is always, you have basically, when you go to do an update, you have an ID, or a number, a version number of the last transaction that occurred. And so when you process an update from somewhere else or an insert, an event, if that number isn't one above, right, if it's behind or, like 3 above, then you have to reject it. I mean, that's a simple way to do it. Obviously, something like GitHub can't do that, right? They have to have a much more complex merge process if it's going to be automatic. And then the other question is versioning of events. And what I would tell you is, in my experience, my event model, once it is established, doesn't change too much. Yeah, it changes a little bit, but it doesn't change too much. And so what we always did is, if we had update employee name, and then we added another field to that event, we just created a new event, version 2. And then our event handler understood the difference. That way we didn't have to worry about replaying or relying on protobuf or something like that to manage it for us. We just knew it would work. It's a little risky to do that if you're going to have tons of changes to your events. Then you may not want to do that, but that worked out real well for us. So, thank you.